Flow-based generative modeling techniques power some of the most popular generative models out there. In this video, we'll cover the core ideas behind flow-based models before covering flow matching in the next one. We'll dive deep into vector fields, ordinary differential equations, and build a simple continuous normalizing flows model. As with our previous videos on generative models, our goal remains the same. Start with samples from a simple distribution and transform them into samples from target data distribution. So with that goal in mind, let's talk about vector fields and ODEs and how they connect to our objective of transforming distributions. If you assign a vector to every point in space, what you get is a vector field. Imagine a 2D plane where each point has both a direction and a magnitude attached to it. For clarity, instead of scaling arrow lengths, we'll use color to represent the magnitude of vectors. Now, what do these vectors actually represent? Well, that depends on the system that we are modeling. In our case, we'll focus on velocity vector fields, where the vector at each point represents the velocity at that point. To make this concrete, think of sand particles scattered across the plane, with wind blowing over them. The arrows of vector field represents the wind's speed and direction. In regions where the wind is strong, so large magnitude vectors, the sand particles will move farther in a given amount of time. In regions where the wind is weak, small magnitude vectors, the particles will only move slightly. So because of this continuous wind or vector field being present throughout time, we end up getting a flow of particles. If at time t equals 0, we start with the initial state of a set of sand particles, the vector field dictates their trajectories over time. Specifically, the magnitude and direction of the vector field determines how each sand particle moves. Furthermore, the vector field that we are seeing on the screen right now isn't time dependent. It's defined as minus y minus x. This means the x component of velocity is the negative of particles' y coordinate and the y component of velocity is the negative of particles' x coordinate. If a particle is at a position with large x and y values, it will have large velocity directed towards the origin. Whereas if the y coordinate of the particle is 0, it will only have a velocity in the y direction. But this vector field could also be time dependent. After all, wind doesn't blow in the same direction at all times. Now, how do we formalize this mathematically? We can describe each particle's position as a function of time. Let's say z of t, which consists of two elements, xt and yt, representing the spatial position of a particle as a function of time. The velocity vector field tells us the rate of change of this position. We can express this as dz by dt equals f of z comma t, where f provides the velocity vector at position zt at time t. For the time independent vector field which we saw earlier, this becomes dz by dt equals minus y minus x. This equation captures exactly what we have been describing. At each moment, the particle moves in the direction given by the vector field at its current position. This is called an ordinary differential equation, or ODE, because it describes the relationship between a quantity and its rate of change, in our case the particle's position and its velocity, and it's called ordinary because we are working with a single independent variable, time. By independent, I mean that it does not depend on any other variable. Time moves forward continuously regardless of the position of particle that we are tracking. Now let's move our focus from vector fields to this ordinary differential equation. To keep things simple, let's assume our particles live in one dimension. We'll describe a particle's position at time t as xt and define the rate of change of position as xt times t. So that means the velocity is given by the product of particle's current position and time. This differential equation describes the relationship between xt, which is unknown, and its rate of change. Solving this ODE means finding the function xt that satisfies this relationship. How do we do that? Well, in this case, we can separate the terms involving x on one side and those involving t on the other side. Then integrating both sides gives us an expression for xt. The expression still contains a constant c. Now what if we were given some extra information? For example, suppose we know that at t equals 0, the particle's position is 2. That is x of 0 equals 2. That tells us exactly what c must be. With that additional information, we can determine the particle's position at any time t. This is what's called an initial value problem. Given an ODE and an initial state of the system at time t0, what is the state of system at a later time t1? In our specific example, given the position of particle at t equals 0 and the ODE describing the rate of change of its position, what is its position at time t1? By the way, we could also express xt1 using calculus like this. All we are doing here is saying that the change in position of x from t0 to t1 can be expressed as the accumulation of tiny changes in position over that time interval. Each tiny change comes from the velocity, and the integral just sums up all of these small contributions across time. Rearranging terms, we can write this expression. So once we have an expression for xt1, we can trace out the entire trajectory of a particle starting from its initial state. Now let's take a step back to our bigger goal, transforming distributions. We started with vector fields, moved to ODEs, and now to trajectories. Why? Because if we sample points from a simple distribution, we can use the vector field to transport those points throughout time. If we design a vector field such that by time t equals 1, those transported points match the data distribution, then what we have is basically a generative model. All we need to do is keep sampling from the simple distribution and solve the ODE to see where those samples end up. There's actually another powerful benefit of using ODEs. To see that, let's revisit our specific example. We solved this ODE and found that C is determined by the initial condition. In fact, C is just the particle's position at t equals 0. Now notice something important. This solution isn't just one curve. It's a whole family of solutions, each corresponding to a different choice of initial value, x0. If we plot one solution, say with x0 equals 2, we get the trajectory that we saw earlier. But if we change the initial condition and plot solutions for many different values of x0, we'll see an entire family of trajectories. Two key observations stand out. The family of solutions fills the entire space. So every point in space lies on some trajectory. The second is that the solutions never overlap, which means each point in space will lie exactly on one trajectory. So given an initial state, the ODE determines a unique trajectory and a unique final state. And conversely, given a final state, there's a unique trajectory and initial condition that leads to it. From a generative modeling perspective, this is amazing. Imagine if we have a vector field that transforms Gaussian noise into samples from our dataset. For every Gaussian sample, there is a unique trajectory that produces a unique data point, and for every data point, there is a unique latent sample that maps back to it. This one-to-one invertible mapping is exactly what we needed when designing normalizing flow models, where we carefully build neural networks to ensure invertibility. But with ODE-based modeling, invertibility comes for free. In fact, the process is fully reversible. Just like we can evolve a sample forward from t equals 0 to t equals 1, we can also run the dynamics backward from t equals 1 to t equals 0. The only thing that is going to change is the limits of integration. Now you might be wondering, this all sounds great, but how do we actually find or learn such a vector field? That is the key question, and we'll get to it soon. But there is another challenge in solving ODEs, even when you know F. Up to this point, we assume that the ODEs that we wrote down could be solved exactly, giving us neat closed form solutions. But in practice, when F is more complicated, analytically solving them, so integrating them to get an expression for xt, isn't always feasible. In such cases, we turn to numerical solvers, which give approximate solutions. The simplest one is Euler. To understand Euler, let's recall the definition of the derivative of xt. Dx by dt equals x of t plus h minus xt divided by h in the limit h tends to 0. If we don't take the limit, but instead keep h finite and small, we get an approximation. In other words, we can approximate the next position as current position plus a small step of size h in the direction of slope. For our case, where xt is the position of particle at time t, dx by dt comes from our velocity vector field. So x of t plus h can be approximated as x of t plus h times f of x comma t. This is the Euler update rule. So how do we solve an initial problem with this? We start with the initial condition xt0, use the update rule to approximate x of t0 plus h, that is starting from the initial state of particle, follow the local slope for a small time h. At time step t, given that the step size is h and the slope is returned by f, x of t plus h is going to be xt plus h times f of xt. Now that we are at xt plus h, we repeat the same step to get x of t plus 2h and keep on doing this in step sizes of h till we reach the final time t1. This will give us an approximate solution to our initial value problem, and how good that approximation is will depend heavily on the step size. If h is too large, the trajectory can drift far from the true solution, and as h becomes smaller and smaller, the approximation gets closer to the true trajectory, though it also becomes more computationally expensive. Euler is one of the simplest ODE solvers, and we actually have a huge list of options to choose from, some of them being much more accurate than Euler, but also compute heavy. So we have seen that when we know f, then even if we cannot analytically integrate it, we can still reach to an approximate solution. Which brings us to our next and most important question. What if we don't know f? And like most situations in deep learning, we are going to learn it via a neural network. For this section, we are going to be looking at aspects from Neural ODE paper and understand how to build a flow-based generative model. Specifically, we'll be looking at continuous normalizing flows. So far, we had assumed that we know the function f, which defines the dynamics of the system. But now a neural network is going to define the dynamics for us. That is how particles are going to evolve from their initial state, hence the name Neural ODE. Our neural network is going to take the input, which will be xt, that is position of particle at time t, and the time step t, and it will produce the rate of change of x as the output. Let's say we have the position of our particles or samples at t equals 0, and we also have their ground truth final state at t equals 1. Then here is what we will do. We'll initialize our neural network with some random parameter values, feed the initial state at t equals 0 to our ODE solver, so something like Euler. The ODE solver will give us the state of these particles at the end time, say t equals 1. But obviously, as of now, the network hasn't learned anything, so the final states predicted by the network will be very different from the ground truth final states. Using some loss on the final state values provided by the ODE solver and the ground truth final state, we train our neural network. Slowly, the network will learn to produce such a vector field that when we use our ODE solver, we end up with the ground truth final state of particles. Like for this problem, where our inputs are samples from standard normal distribution and target distribution has points scattered around the boundary of this circular region. For this, our network should ultimately learn such a vector field, where we can see that particles inside the ground truth circular region are pushed to the boundary and particles outside are pulled inward, to ensure that the network predicts the same final state of these particles as the ground truth final states. Now, obviously, when we are talking about transforming simple distributions to data distribution, we don't really know which initial latent sample will be transformed to which data point. So we'll just use maximum likelihood for training. We'll first come up with an expression for log likelihood of the data points, and then train our model to assign higher likelihoods to these points. This is exactly what we did in our previous video on normalizing flows. I'll just repeat some of the details of normalizing flows here in case you have not seen that video. In normalizing flow, we have our samples x from data distribution and samples z from simple distribution like standard normal. We also have n invertible neural network layers, which in a sequence of n discrete steps learns to transform samples from one distribution to the other. During training, we took the data point x, which was just Zn, and transformed them to Zn minus 1, Zn minus 2, all the way till Z0. Then using change of variable theorem, our log likelihood of data point x ended up being log likelihood of Z0 plus summation of log determinant of Jacobian of all the n transformation layers. Since we want to have the model assign high likelihood to the data points, we simply feed the data point to our neural network layers and keep track of the summation of these log determinant terms and also the final Z0 latent that our network ended up computing for the given data point. Since Z0 would just have a Gaussian distribution, we can easily get an expression for log p Z0, and that plus the log determinant terms becomes our log likelihood of data point, and we train our model to maximize this value. For sampling, once we have trained the model, we can take samples from initial simple distribution and have it flow through the inverse of the learned transformation layers to get a generated data point. This was all about normalizing flows. In continuous normalizing flows, rather than having this discrete set of layers, we have a continuous time transformation. During training, we take the data point Zn at t equals 0 and using the ODE solver and neural network, transform it to Z0 at a final time capital T. Our neural network is going to be predicting dz by dt with theta being its parameters, and the ODE solver will take care of accumulating those small changes predicted by the network and transport particles or sample points from initial state to some final state. When we were working with discrete sequence of layers, the change in log probability was the log determinant of Jacobian. The authors of Neural ODE show that in continuous time case, the change in log probability follows a differential equation, with its rate of change being equal to the negative of trace of Jacobian, under some mild assumptions. The authors also give a proof of this in the appendix of the paper, where they use change of variables theorem, which we covered in much detail in the previous video, as well as the definition of derivative. So in case you want to have a complete understanding of the proof, do go through it. Now using calculus, we can compute the change in log probability from t0 to t1 by integrating this rate of change of log probability over time. This is same as expressing change in xt from t0 to t1 by integrating dx by dt over time. Since the rate of change of log probability is negative of trace of Jacobian, we get this expression. As during training, we start with data point x at t0 and at t1 or final time, we have our sample z from simple latent distribution. We can rewrite this expression as this, which means both the final z during training and change in log probability from data point x to z0 can be obtained by solving their respective ODEs. In practice, rather than solving two separate ODEs, we just solve one and use an augmented system, where we are not just evolving zt, but we are also keeping track of the change in log density. The initial value of this augmented system is x and 0, where x is the data point and 0 is the initial value of log density change. So once we solve this ODE, we end up with the final z, which will be our latent point from simple distribution, and also the accumulated change in log probability from data point x to the computed latent point z. From this change, we can compute log px and train using negative log likelihood loss. This ensures that our network ends up producing such a vector field that points from our dataset are transformed to high likelihood latent points. To make sure that we have understood everything about continuous normalizing flows, let's look at the code to train this flow model on a synthetic dataset. This is a very simple implementation of continuous normalizing flows, bringing in together everything that we have seen so far in the video. It's only about 100 lines of code, and we are going to be training on the 2D synthetic moons dataset from scikit-learn. For ODE related code, we are going to use this torch differential equation package, which will take care of solving the ODE for us using our choice of solver. We first have a bunch of constants. For most of them, the name should clarify what that constant represents. Our dataset is a 2D dataset, so the dimensionality of data will be 2. And we are going to be training on 2000 data points with a model that only has linear layers, with the hidden layer size being 64. Obviously, the input and final layer's output size will be the same since all z's will have the same dimensionality, which will be our dimensionality of data. Our ODE solver will be integrating over equally spaced 50 steps from 0 to 1 during training, and during sampling, it will be going back from 1 to 0. This is our model class, and in here we initialize the layers, which, as I said, linear layers with some nonlinear activation. The input is going to be 1 plus data dimensionality. That's because our model is going to take time and z underscore t as input to compute dz by dt. So we are just going to concat the time and z inputs together, making the input size to our model batch size cross 3. And obviously the output is still going to be batch size cross 2. Let's move to our forward method. So this is going to be called during training as well as sampling. Its inputs will be initial z, start time and end time, and number of time steps in the sequence. During training, we'll have start time as 0 and end time as 1, and z will be our data points. And during sampling, start and end time will be flipped, with z being sample from standard normal distribution. Inside this method, we first create our time step sequence. By default, these would be in increments or decrements of 0.02, so 1 by 50. Here we are initializing our augmented state. During training, at t equals 0, our delta log p will be initialized as 0, and ultimately ODE solver will accumulate delta log p over entire time step sequences. So our augmented state is just data point and 0. This part is where we'll call our ODE solver, passing it this ODE func method, which is going to compute our dz by dt and d log p by dt. And we are just choosing to use Euler for this simple dataset. The ODE solver finally returns the sequence of augmented states for all time steps. Zt in our case would be 50 cross 256 cross 2. Because we have 50 steps in the time sequence, 256 is our batch size and 2 is the dimension of data. Let's look inside this ODE func method before proceeding with the rest of forward code. The ODE solver is going to be calling our method with the time step and current augmented state at that time step. We first get zt from our augmented state and compute dz by dt. For this, we call our linear layers. We also need to compute d log p by dt, and for this we need trace. For trace, we first initialize an all-zero tensor of same size as batch size, and then loop over the dimensions one by one. In the ith iteration of this loop, we'll compute partial fi by partial zi, so the ith diagonal entry of our Jacobian, and sum of all these ith entries will be our trace. We get the partials using autograd.grad. This sum here ensures that our output is a scalar quantity, and obviously one batch item will not affect other batches' output, so ultimately after this call, we'll get a matrix of batch size cross dimension of data. This will be partial fi by partial z for all the data points in the batch. And from that we get the ith entry, which will be partial fi by partial zi. Ultimately we keep accumulating these terms to get our trace. D log p by dt is negative of trace of Jacobian, so that is what we return together with dz by dt. Back to forward method. This ODE integration call will integrate and give us zt's and delta log p's for all time steps. The final state will be our predicted z0. So to get log likelihood of z0, we use the expression of standard normal to compute log p z0. Delta log p would have accumulated log probability changes. So from t equals 0 to t equals 1, we would have gone from data point to z0, which means log p z0 minus log p data point equals delta log p. So log likelihood of data point is just log likelihood of z0 minus delta log p. During training, we return this, and in our training loop, we'll use this to compute negative log likelihood loss and try to minimize that quantity. The same forward method is also called during sample. In sampling, everything is same, except that now we'll be going backwards in time from t equals 1 to t equals 0. So to the forward method, we'll pass start time as 1 and end time as 0. And then finally just return the last state of backward sequence, which will be our generated sample. The actual sample method is down here, which will start with the first state of backward sequence, so samples from standard normal, and call our forward method with start time as 1 and end time as 0, and return the 0th time state data, which could be our generated sample. These lines are just for creating the dataset, and here we instantiate our model, optimizer, and loop over all epochs and train using negative log likelihood. This forward call during training returns the log likelihood of data point, so negative of that becomes our loss. Once trained, we call our sample method and look at the generated samples. When we look at all the 50 time steps of all the sample points, we can see that the model learns to progressively transport samples of normal distribution from their initial state to points which look like samples from our moon's dataset. And this entire code that we implemented works, but it has two drawbacks: high memory usage and the computation of trace. For our case of small network and the data dimensionality also being small, this wasn't an issue. But in practice, we do need few changes to make the implementation more efficient. This section isn't really important to understand flows, but I have added it for completeness sake. Let's first look at trace computation. The overall complexity of trace computation is big O of d squared, where d is the dimensionality of data. Using something called Hutchinson's trace estimator, we can approximate the trace of our Jacobian matrix without dealing with that quadratic complexity. Instead of directly computing trace of a matrix A, we can estimate it as the expectation of E transpose AE, where E is a d-dimensional random vector with zero mean and unit variance. So something like samples from standard normal also works. Earlier, we were computing the Jacobian of a d-dimensional output with respect to d-dimensional input, which led to quadratic complexity. But with this trace estimator, we only need the Jacobian of a scalar with respect to d-dimensional input, reducing the complexity to big O of d. Moving to the next problem, memory. And let's understand why there is a problem in the first place. In the forward pass, the ODE solver integrates through all time steps until we reach the final time step, and we compute loss from this final state. But every intermediate state depends on the parameters theta of our neural network. So to compute gradients, backprop would need to save all activations across all time steps, causing a huge memory load. To avoid this, the authors of Neural ODE paper use the adjoint method. The key trick is this: instead of storing everything, we can solve a backward ODE that directly tells us how the loss depends on trajectory. We only need the final state to start this backward ODE, ensuring that we don't really need to save the states for all time steps. The adjoint at a given time t is essentially the sensitivity of loss to the state at that time. For the final state z of capital T, we get this as its adjoint. The authors show that this adjoint state evolves according to its own ODE. So just like the forward trajectory, we can also integrate this adjoint ODE backwards in time from t equals capital T to 0, recovering how the loss depends on all earlier states without having to store all the state information. The gradient for parameters can then be accumulated according to this integral. Intuitively, the adjoint tells us how sensitive the loss is to the state at time t. The Jacobian of the dynamics with respect to parameters tells us how the state changes when parameters change. Multiplying the two and integrating across time, we get the gradients of loss with respect to parameters. Let's summarize the high-level steps of using adjoint method. We first use the ODE solver to integrate from initial state z0 to final state z capital T. Compute the loss from final state, and in our continuous normalizing flows case, we have to also add the trace term here. We'll then initialize the adjoint for the final time step using autograd.grad with loss and the final state. And we'll also initialize an accumulator for gradients with respect to parameters. We'll keep adding the gradients for parameters from all time steps to this accumulator. Then we move to the necessary steps for backward pass. We are going to go backwards in time from t to 0. For each time step t in the sequence, we first compute Jacobians with respect to parameters and state at time t. Assuming d as dimensionality of z's and p being the number of parameters, these would be d cross p and d cross d shape. We would then compute the adjoint for time step t. This would look similar to Euler, where you use adjoint at time step t plus dt, so the previous time step in backward sequence, and Jacobian with respect to state to compute change in adjoint. We then add in gradients for this time step using adjoint and Jacobian with respect to parameters. And after completing the backward sequence, we have our required gradients. At a high level, these are the steps involved to compute gradients using adjoint method. And from an implementation perspective, this entire process is wrapped for us in the ODE int underscore adjoint method from the Torch differential equation package. The authors provide a proof of all this in the appendix, where they show that the adjoint state follows the given dynamics. However, I found that looking at the ODE training as a constrained optimization problem and then using Lagrange multipliers to get an expression for computing gradients is easier to digest. Basically, we have our task of minimizing the loss and we have constraints in form of our ODE for all the time steps. Then we can write the Lagrangian for this with lambda t being the continuous time Lagrange parameters. It turns out that the specific value for the Lagrange multiplier for each time step is nothing but the adjoint state for each time step. And the ODE for the adjoint together with the gradient expression also comes out as a result of that. I found this video which goes into the full derivation step by step. So please do take a look at this. I've added its link in description. There are also a couple of other playlists which you can take a look at if you want to go deeper into adjoint, and I've added those as well in description. Okay, so that brings us to the end of this video. In the next part, we'll further simplify training of flow models. As of now, we need to solve the ODE during training. But in next video, we'll see how we can do better and make it less costly. So see you then. And thank you for watching this video.